Hello, everyone. Hope you're all doing well. Let's try this out. See how this works. So I'm going to go over the handout from yesterday that was due today. This one is on our rules of exponents, which hopefully you watched the video and saw what the rules were. But let me go over this. So we have 2m squared times 2m to the third power. The first thing we look at are the coefficients, which are just the whole numbers. We have a 2 here and a 2 here. And we multiply them because the operation is multiplication. 2 times 2 is 4. Done. Fine. Then we've got m squared and m to the third power. The rule is when multiplying common bases, we keep the base. So we have m squared times m to the third. We're going to keep the base as m. And when we're multiplying, what we do is we add the exponents together. So we get m to the power of 2 plus 3, which is m to the fifth power, which gives us a final answer of 4m to the fifth power. That's the first one. For the second one, we're going to do the same thing, and we'll deal with that negative exponent at the end. But to start, we do the 4 times the 2, which gets us our 8. Okay, those are the coefficients in front. We're multiplying them because this is a multiplication problem. Then we have r to the negative third power times r squared. We have the same base being multiplied, so we keep the r, and we add the exponents, which is negative 3 plus 2, which gives us r to the negative first power. So we have 8 times r to the negative first power. Now, with a negative exponent, what that means is we're going to move that to kind of like the denominator, is one way to think about it. What it really means is we're going to take the reciprocal, but that's the lesson that was on Tuesday the 17th. So we'll talk more about that then. But we have 8r to the negative first power, which just means we keep the 8 as is, because that's not being raised to the negative 1 power. And the r moves to the denominator. So we get a final answer of 8 over r. For the third problem, we have 2k to the fourth times 4k. Again, 2 times 4 gives us our 8. K to the fourth times k. Well, k alone is really k to the first power, if you want to think of it that way. So, oh, my pen's not working. There we go. All right. So we got k to the fourth times k to the first. See, this is what happens. I let my daughter use my pen, and now it's not writing. There we go. And then we have k to the power of 4 plus 1. 4 plus 1 is 5, so we have 8k to the fifth power. Okay, for number 7, the other one that I had a couple of questions on, we have 2 times 3 just as before, which keeps it 6, okay? Now, this is a y. This is an x. Those are not the same basis, so they have nothing to do with each other. Think of them as not unlike terms. So we have 2 times 3 is 6. That's where that 6 comes from. And then we just keep it. X, y squared. So 6xy squared. For number 9, we've got this funky looking problem. We've got 4a to the third power b squared times 3a to the negative fourth b to the negative third. Don't freak out with the negatives just yet. You can freak out later, but for now, don't. Just keep doing the same rule. 4 times 3 gives us our 12. Okay? Then deal with just our like terms. We have the a to the third and a to the negative fourth. Multiplying common bases, keep the base a, add the exponents. 3 plus negative 4 is negative 1. So we've got a to the negative first power. Then we do the same thing with the b's. B squared times b to the negative third is b to the 2 plus negative 3, which is b to the negative 1. So that gives us 12, a to the negative 1, b to the negative 1. So that's why we have 12, a to the negative 1, b to the negative 1. Now, the only ones that are being raised to that negative first power are the a and the b. The 12 is not being raised to the negative exponent, so it stays where it is, and the a and the b move downstairs, and they're being multiplied together because that's the operation here. So it's 12 over a to the power of b. I'm sorry, a to the b. A times b. For number 11, we've got x squared to the power of 0. Anything that ends in a power of 0, especially in parentheses, because the parentheses means everything's being raised to the power of 0. Well, guess what? Anything raised to the power of 0 is 1, so it just turns to 1. Doesn't matter what's inside here. It could be a smiley face. It could be anything. Anything to the power of 0 is 1. For number 13, so similarly, anything to the power of 0 is 1. However, what's being raised to that power of 0 is just the r. So it's 4 times, well, r to the 0 is 1, gives us 4 times 1. And then that's being raised to the fourth power. Our order of operations tells us we do what's inside the parentheses first. 4 times 1 is just 4. And 4 to the fourth power is 256. And lastly, we've got 3k to the fourth raised to the fourth power. Okay, this is I call it the expanded power rule, where everything gets that exponent of 4. So we have 3 to the fourth power times k to the fourth power, because there was k to the fourth power here, and then that's being raised to the fourth power. So 3 to the fourth power is just 3 times 3 times 3 times 3, which is 81. Now the power rule states anytime you have an exponent raised to an exponent, you multiply them. So we got k to the power of 4 times 4, which gives us a final answer of 81k to the 16th. All right. I hope this worked out well. You can please give me feedback. Let me know if this is good or it's bad, and I'll continue to do it. So if you have any questions, let me know, and I'll talk to you guys later.